So in the next section, I want to convince you that the LCP array is not only useful, but also quite easy to compute. Let's first take a look at what we could do just naively. How do we fill the LCP array, and how long would that take? By definition, each entry in the LCP array is the longest common prefix of two suffixes. So I could do just take the two suffixes and compare them character by character and count how long the characters are equal. That's fine, but in a contrived example, like the text with all A's is the worst case for most of these things, you always have to walk till the end. And so this could take linear time for one check and quadratic time in total. So that's not brilliant. The insight here is that if you ever see a big value in the LCP array, you will be guaranteed to see other big values. So there's, in a way, a charging scheme behind this. If you have ever had to go a long way of comparing, then there's a way to make that knowledge pay off in the future. That's an idea vaguely that at this level of abstraction, we've used it before, amortization. But let me illustrate in an example why this is promising. And so here the text is this, I don't know if you know this famous English, it's a valid English sentence just because English is so great in ambiguity. The full version is buffalo, 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 buffalo. Proper English sentence, you can look it up. I went for the slightly shorter version here, just to make the point. Suppose you try to find the, so you've constructed some of the suffixes in sorted order. That's the first suffix, that's the next in sorted order, in lexicographic order than this one. And so these two, you would now like to know the longest common prefix. So all right, here you go. They are pretty much identical up to the dollar. So that would have been an LCP value that you would have to pay for a lot because you need to compare all those characters. But if we have these two really similar strings that start with a long common prefix, if I throw away the first character, the rest of the remaining 18 characters are still the same. So somewhere in the suffix array, I have these suffixes where the first character is missing and the rest is the same. And they still have this longest common prefix. It's just one shorter. Okay. Now, it's unclear where those are, and it's unclear where to put this value 18. And even worse, it's not clear if there is ever a value at 18 exactly. The problem is that if you chop off the first character, you don't no longer know if these two suffixes are adjacent. There could be others that are between them. And you only have LCP values for two adjacent suffixes. But the same idea can still be made to work. And that's the algorithm I want to present to you now. It kind of uses this idea, but in a slightly smarter way by turning things on the head, if you want. The key idea of this algorithm is to compute the LCP values not in the order of the suffix array, like LCP1, LCP2, LCP3, and so on, but computing them in text order. So what this means is shown in this picture again. Text order is on the left. And so the first thing you want to do is compute the LCP value for the first suffix. This LCP value where this, the longest text participates in. And then we can drop the first character. This might not be directly what we need, but we can make sure that we don't throw away knowledge. So I think this is clearest in the example. So we go through the suffixes in text order. So we start with the one that starts at position 0. We use the the right array, the rank array, to see that this occurs at position 6 in the sorted list. Okay? So that tells us which LCP value we're actually trying to compute first, because it must be the one between the suffix here and its predecessor in sorted order. And so that happens to be the suffix starting at 6. And then the algorithm naively compares. So we started the first character, these match, so they are shared. Longest common prefix continues, continues. We found those 3. Then the next one differs. So the longest common prefix between those 2 is 3. So far, nothing smart happened, right? We just compared naively. And we can fill the first entry in the LCP array, namely the one that corresponds to the longest suffix. Okay. Now, what happens if we remove the first character from both of these suffixes? Well, of course, the longest common prefix is 1 shorter. But there is another thing that happens. If I remove the first character, I get to the 1 smaller suffix of the text. So instead of the entire text, I'm now looking at this one. I didn't want to strike this out. This one. So that's the next one to look at. And we remember that we've matched 2 characters in the previous comparison after we deleted the first one. Okay, so same game again. We start from scratch. We have this one. The rank array says it occurs at position 4 in the sorted list. So that's where we go. And so the next LCP array entry will be the one at position 4. And we compare this string with its predecessor in the sorted list. Now notice that this ban with B deleted is not the predecessor. It's one that comes before it. That's one of the cases that I warned you before. There could be other suffixes that now lie between those 2. But we still know that this one and this one, they shared a common prefix of 2. And so if this new string is between them in sorted order, it also has to start with AN, otherwise it couldn't be at this position. So in fact, all the strings between this one, the shortened predecessor from before, and the shortened suffix we're looking at, all of those in this range must start with AN. So we inherited this longest common prefix of AN. We don't have to check it again. That's why it's shown green. We know that 2 first characters must be equal. And we just compare with the ones afterwards. In this case, the A matches, but then we have a mismatch. So we have another entry of 3. Okay? Kind of see how this goes? Let's do one more. If we chop off another character, then we're at this position. The rank array says that occurs in position 9 in the sorted list. So that's where we go. We try to find their longest common prefix. And we know from before, we don't have to check the first 2 characters because they must be the same. If this and this agreed on the first 2, on the first 3, after deleting the first one, these still agree on the first 2. And so really what's happening is just we take the previous LCP value we wrote and subtract 1. You don't really have to check which suffixes are involved, etc. That was just for explanation. The algorithm just says, okay, I know 3 was the last value, so 2 are definitely the same. I don't have to check. And then you keep reading. This time we have a mismatch here, so we leave it at that. And let's do another one. So they become faster and faster now. That happens to be at position 3 here. So we have to compare those 2 and find the longest common prefix. We know by the last value that we wrote that at least the A matches. Now in this case, we can continue it by 1 more. So we indeed have a 2 again, but that's it. So then we go to the next position in the text, this one. We find it in the sorted list at rank 8. We know they have at least 1 character in common. And if we compare 1 more, we find out that's the only one. So we write a 1. Okay? And that's how it goes. For this one, we know from before, we know nothing. It's only 1 minus 1 is 0. So we have to start comparing. We find there's actually nothing in between, so that remains a 0. Next character, we find where it is in the sorted list. We know nothing, and we compare, and there is nothing, so it's another 0. Let me go to this guy. Here again, we know nothing, but we find overlap of 1. So we write that there. And, well, 2 more. And so for the last one, we actually don't have to do anything because the one that has rank 0 is the first in this list, and so there's no predecessor. And that always happens to be the suffix with just the $sign. So we can just stop at one early. Okay, that's Kasai's algorithm for computing these LCP values. Because we've done the example in great detail, I don't want to go through the code in detail. That's exactly spelling out the same idea. I don't think it reads well in the code. The example is much clearer. There's just the one thing I want to point out. You keep track in L of the length of the longest common prefix. So L is this value that we wrote at the end in the current LCP array entry. And then we subtract 1, but never go below 0. So that in the next iteration, when you start comparing at L and not with the first characters. That's exactly what we did in the example, skipping the green parts. Let's briefly think about why this algorithm is linear time, though. And what we'll look at is the number of character comparisons, because that's the dominant operation in finding the common prefixes. And the trick for the analysis is to separately count those that come out as equal and those that come out as non-equal. It's just easier to count them separately. Every character comparison that comes out as not equal must be the end of a common prefix. So that's where we detect, no, they don't share any more characters. And this can happen only once for every LCP array entry because we stop after that. That's something that's obvious in the code. You ask, are they still equal? And if not, then you continue with the next iteration. So we have at most n of those, at most as many as LCP array entries. The interesting ones are the ones that come out as equal because they might be frequent. You might have to compare many long prefixes. But whenever you do have one of these characters comparisons that come out as equal, you increment L. That's obvious again in the code at this point. You increment L. But L can be at most n because it's the length of the string. And we decrement it at only one position, and we do that only once for each outer loop iteration. So it's never decremented more than n times. So the largest number of equal comparisons you could ever have is 2n, because you could go up to n and then be reduced down, but that's it. Okay, and that leads us to linear time overall. The argument here is quite similar to what we've had for the KMP algorithm in Unit 4 and for other methods. It's oftentimes a similar kind of argument. You have some potential that is built up slowly, and you just can pay much in one iteration, but it has to be then followed by many cheap ones. That's the end of the suffix array construction. And to finally bring this long unit to a close, I want to point out that we have solved this first big magic black box that we started with at the beginning, because we can now finally compute suffix trees and in linear time. And you've seen all the details for that. We can compute the suffix array for t. It took us the better half of today and a bit of build up before to go through the algorithm, but the DC3 algorithm shows you how to do this in linear time. We've seen Kasai's algorithm for the LCP array just now, still linear time. And from those two, you can actually figure out the suffix tree using this idea of LCP intervals. I haven't shown you the details. You will practice it on an example in the tutorials. And it will essentially close the loop in Unit 9 with the concept of the Cartesian trees. So maybe if we have enough time, I'll point it out there in more detail. If not, then take my word for step 3. You can relatively easily piece together the two arrays and build the suffix tree if you want to. It's a legitimate question, though, if you ever have to build the suffix tree as opposed to staying with the two arrays. That's my last point for this one. These two things together, the suffix array and the LCP array, and sometimes a few extra data structures to help work efficiently with them. That's called the enhanced suffix array. And in a way, that's the modern version of suffix trees. The only downside I see is that it is more complicated to reason about because it's just these lists of numbers, and you always have to keep in mind what is L and R and all these things. But you can support the same operations as in suffix trees, and there's even an automatic way. If you came up with an algorithm for suffix trees, you can translate it to one that works on the arrays in a schematic fashion. It uses much less space compared to the tree, especially if you do it in the easy way. And we have a arguably simpler linear time construction, at least one that I dare to present to you in a lecture, whereas the suffix tree ones are questionable. They are even more intricate. So we've seen all the details of text indexing, building the enhanced suffix array of a text, and then you can do all sorts of cool searches and analysis on the text. And that's the basis for many things. One pointer for current directions is to reduce the space even further. So you can do all that we've seen if you also try to zip the text. So you try to compress the text, but at the same time keep all the functionality we've seen. And that kind of all builds on these ideas. So that's still worked on a lot and is what you need to do if you have genomic databases where you don't have just the genome of one person, but of 1,000 people or even more. Then you need to compress. Otherwise, you just don't have the space to store that. And that leads into the next unit where we look at compression without combining it with this unit, but we'll do the basics for that part as well.